Welcome back to my channel Shri Statistics. Now today we are going to talk about a theorem. This theorem states that if A be an n-row non-zero real matrix of rank R, then there exists a non-singular matrix P such that P transpose AP is equal to the diagonal matrix which contains 1, minus 1 and 0. Supposing that 1 appears S times, minus 1 appears R minus S times. Also for all real non-singular matrices P, such that P transpose AP is a diagonal matrix whose R non-zero diagonal elements are the numbers 1 and minus 1, and the numbers S and R minus S, which denote respectively the number of times 1 and minus 1 appear, are constants. So to prove this, A is said to be a symmetric matrix over the field of real numbers. Therefore, there exists a non-singular matrix Q such that Q transpose AQ is a diagonal matrix with R non-zero diagonal terms. Let Q transpose AQ is equal to this diagonal matrix, that is B1, which contains up till BR elements and the rest are 0. Suppose that S of the non-zero elements over here are positive, so that R minus S of these remaining elements, there are total of R, and if we take S as the number of positive elements, then the remaining will be negative. So the following elementary congruent transformations are performed on the diagonal matrix, that is this Q transpose AQ, interchanging the ith and jth rows and the ith and jth columns in such a manner that the congruent diagonal matrix is obtained with the first S diagonal elements positive and the next R minus S diagonal elements are negative. Now we can state without loss of generality that the numbers we have assumed B1 up till BS can be assumed to be positive and the numbers BS plus 1 up till BR to be negative. So as a consequence, it can be assumed that there exists R real numbers, that is capital B1 up till BR, such that B1 square is equal to this value B1 from here, and BS square can be equal to BS, and BS plus 1 square onwards, this becomes minus BS plus 1 because the remaining the values were negative. So up till BR minus BR. So if R is capital R is considered as the diagonal matrix of these, that is this B1 inverse, B2 inverse, BR inverse and the ones, and then taking P is equal to QR, you would recall from the previous value of Q, we substitute this value of R and the value of Q which was stated here, this. So on taking these, we come over to solving this equation. So on solving this, here this becomes P prime AP is equal to R prime Q prime, because this is being taken as the transpose, and over here A and RQ. And so on substituting the values and solving, we get this diagonal matrix which consists of 1 and minus 1 and 0, so that 1 and minus 1 appear S and R minus S times respectively. So this proves our theorem. So that's all from me for today. If you like the video, please share and subscribe. Thank you for watching.